Okay, welcome to the webinar. We'll wait a few minutes until all the participants are allowed to enter in the webinar. Okay, so welcome to everyone to the workshop on next generation quantum clock. This workshop is organized in the framework of three different European projects, USOQS, CLOCKS, and CC4C, that are a project of Quantera program and Empire program led by Euramet. So they are all European big consortium. And this workshop is organized by ICFO, that is hosting the webinar in his platform, and Niels Bohr Institute of University of Copenhagen, and INRIM, the National Meteorological Research Institute of Italy. I'm happy to have today the first talk given by Professor Matthew Jones of Durham University. Matt is a professor in quantum light and matter, and his research is focused on the use of highly excited state, Rydberg, so named Rydberg state in quantum optics and quantum metrology. So he will give us a talk about Rydberg clocks. And regarding the webinar, we will have 45 minutes of lecture, and then we have time for question and answer. You can either raise your hand or write a question on the question and answer box that you see in the lower part of your screen. And then I will be able to read the question for you if you prefer to write the question. Otherwise, you can raise your hand and I will give you the right to speak after the seminar. Please, Matt, you can go ahead with the seminar, your presentation.
Okay, that's great. Can everybody hear me okay? Yeah. Well, first of all, I want to give a massive thank you to the organizers for putting together this meeting. I think in this COVID-19 situation, these virtual conferences are hugely important to try and keep us all together, but also to educate the newer people who are joining our teams and who won't have the chance to visit other laboratories for a little while yet. I know it's a lot of work to put one of these together, and I want to thank Filippo and everybody else who was organizing, who's put effort into the organization. So I was asked to talk to you about Rydberg clocks. So this is kind of a bit of a new direction, I guess, both for me and for perhaps the field of clocks. So I have been working on Rydberg atoms for a long time now, but it only became apparent to me a few years ago that maybe there were links to the field of precision metrology and atomic clocks, and I hope to bring that out to you in my talk today. Okay, so I want to start the talk with this slide, plenty of room at the top. Okay, so this is to try and motivate why we might be interested in these Rydberg states. So as quantum physicists or clock scientists, we often forget the details of the atom that we work with. We're obviously very interested in the properties related to our favorite clock transition, and maybe our laser cooling lines as well, but we kind of forget the rest of the identity of the atom that we are dealing with. And I put this diagram up. It's what's known as a Grotrian diagram, so an energy level diagram, up just to remind you of how rich the structure of the atoms that we work with really is, okay? So in this diagram, we have energy starting at 0 for the ground state and going up to the ionization threshold. And then each of the states here is labeled with a term symbol. So we have the spin, singlet for 1, triplet 3 here, and the orbital angular momentum given by a letter and so forth, okay? And over here, we have some more complicated states that I'm not going to talk about very much today, but you can ask me about these at the end. And so some of you who work on optical lattice clocks may have guessed which atom this is the Grothian diagram for. It is, of course, the Grothian diagram for neutral strontium. This is the main cooling transition at 460.7 that anybody who works with strontium would be familiar with. And this is the clock transition. So, of course, clock transitions usually are the lowest lying or the lowest transition in an atom. So there's no surprise here. This is a transition between the ground state and the lowest excited state, which in this case is metastable. And that's what gives us this wonderfully narrow line that we can use for these amazing optical clocks, which are now operate at 10 to the minus 18 or even better, okay? And of course, in the alkalis, the story is similar. There, this would be a hyperfine transition, but again, it is the transition between the two lowest lying energy levels in the atom. And there's a very good reason for this, of course, which is that we want these long-lived states here. We don't want lots of radiative decay channels where this state can decay. We'd like it to be only coupled back down to the ground state, so our clock transition is closed. But there's an awful lot going on up here, and maybe we can use these for something else. And what I want to focus on today is this band that's not even shown in this diagram, so where the so-called Rydberg states live. So these are states with really, really high principal quantum number. They're kind of squashed up against the ionization threshold here. And there's really an infinity of worlds there. So theoretically, at least, there are an infinite number of states here getting closer and closer to the ionization threshold. So we have a very, very rich structure of energy levels, which we can exploit for various things. And so if we zoom in, we might see something like this. Energy levels, they're not quite evenly spaced. Typically, the separation between states of different principal quantum numbers is in the microwave region. So at n equals 50, it's roughly, depending on the atom, between 40 and 80 gigahertz apart here. And there's a great long continuum of these states that we can choose to pick out. So of course, being separated by a few tens of gigahertz means that we can easily resolve one of these energy levels with a laser. And so basically, the question I'm answering in the rest of my talk is there anything we can do if we couple a clock transition down here to some Rydberg states up here? What might we gain from doing this? For example, one could do it by putting on a laser here, which would drive, say, from this triplet P0 transition up to a triplet S Rydberg state. Okay. But we should bear in mind that there's actually a huge range of states that I could choose up here, all with slightly different properties and which can be tailored to the application that I have in mind. So this is what I'm going to talk about in the rest of my talk. I'm going to give you kind of I'm assuming that most people are coming from a clock science perspective, so I'm just going to give you the few things that everybody needs to know about Rydberg atoms. So you'll see that actually the list is remarkably brief. And then for a clock audience, I thought it would be good to talk about how they interact with external fields. Of course, when we're building a clock, once we've chosen which atom we'd like to work with, one of the most important properties we have to think about is what effect external fields have on our clock transition. And we'll see how these two things can work together. One thing that Rydberg atoms bring are very strong long-range interactions, and I'll explain how important they are. And then we'll look at how those interactions can be used to generate entanglement and squeezing. So of course, we had talks on both of these topics yesterday. So this will hopefully follow on nicely from the two tutorial talks that we had yesterday. And then very, very briefly at the end, I won't talk in any detail about these, but some of the new directions that are emerging in this area, which I think could be quite interesting going forward. So the first thing that we should know about Rydberg states is their energy levels. So they are given by a very simple formula, often known as the Rydberg formula. So we have a Rydberg constant on the top here. And for hydrogen, this would just be then divided by n squared, the principal quantum number of the state. For atoms that aren't hydrogen, we have to subtract off this quantity here, delta L. So this quantity here is known as the quantum defect. And it basically encapsulates the fact that our core is not a simple proton, but is actually got some electrons around it. And so there is some screening of the Coulomb interaction. And one way you could think about this is that it just gives a phase shift of the wave function. So if you took a hydrogen Rydberg wave function, then all you would be doing by bouncing it off this electronic core essentially is giving it a bit of a phase shift. So when it penetrates the core, it gets a bit of a phase shift, and this delta here encapsulates that phase shift. So it's large for states with low angular momentum, so S states, and to some extent P states and D states, which overlap with the core. And it's very small. In fact, it goes to 0 as the angular momentum quantum number approaches the principal quantum number. Okay, so as the Rydberg electron overlaps less and less with the core, this quantum defect goes away. And for large L, basically all the atoms look exactly the same as hydrogen. And just a very brief note on this Rydberg constant. This Rydberg constant isn't the one for hydrogen. If you're dealing with strontium, this will be what's called the scaled Rydberg constant, which just includes the effect of the reduced mass. Okay. So from knowing this, you can actually construct a wave function. So here's a plot of a wave function. And the first thing that you notice when you do this is the huge extent. So this is the modulus squared of the radial part of the wave function. So you recall from your basic quantum mechanics that you can factorize the wave function of an atom into a radial part and an angular part, the angular part being given by the spherical harmonics. And this is the radial part then, the modulus squared of the radial part, well, it's actually R times the radial part squared. So the radial probability distribution, if you like, plotted as a function of the radius in units of the Bohr radius, so the size of the ground state of hydrogen. And you see this is for roughly n equals 70. You see that these orbits really are colossal. So the most likely position for the electron is at a distance of nearly 5,000 Bohr radii away from the nucleus. And in fact, you find that this average distance, so this place where you're most likely to find the electron, scales as n squared times the Bohr radius. So you see 70 squared is about 49,000. Sorry, yeah, 49,000. So that matches up with this. And this corresponds to about 200 nanometers in real size. So these atoms, which we normally think of as being 1 or 2 nanometers across, are now large. And in particular, they become large compared to the size of an optical lattice period, for example, which has some interesting effects. And the other important thing that people often don't really associate with Rydberg states, we're used to thinking of excited states having a short lifetime, but actually the radiative lifetime scales as n cubed for these very high lying states. So the higher we go, the more long-lived the state is. And that's again because radiative decay wants to take us back down to a low-lying state, and as the overlap with these low-lying states decreases as n increases, the probability of radiative decay goes down as well. And so these states can be relatively long-lived, with lifetimes of up to about 100 microseconds, again at around n equals 70. So the good news is that you don't actually need to worry about working out what a quantum defect is or where you might find them. There's been a huge amount of work in the Rydberg physics community for bringing all this kind of information together. And I just want to highlight this paper, which comes from our group. So Nicola Sibulic here, who is now working at the Institut d'Optique in Paris, developed a code called ARC, Alkali Rydberg Calculator, that calculated the properties of alkali Rydberg atoms. So it contains all the quantum defects and things, wave functions and things like that. But you can also calculate start maps. We'll see what those are. You can calculate the interactions and so forth. And we've recently added in this paper, which is on the archive now, data for divalent atoms and the mechanics that you need to do this for divalent atoms. So at the moment it includes strontium, calcium, and ytterbium, but there's no reason why. This is a kind of community software project, so other divalent species can easily be added in the future. So if you do need to calculate or find yourself wanting to calculate the properties of Rydberg atoms or explore their energy levels, then I suggest you go and have a look at this code, because it makes it very simple to make a wide range of plots and to explore the structure of these energy levels. So I'm not going to, in Rydberg's 101, it's going to be very short. We're basically going to point out that they're very large, very long-lived, and that the rest of the information that you need, you can get from this kind of software package. Okay, so what about external fields and Rydberg atoms then? So of course in clock science, one important aspect is to minimize the effect of external fields on our clock transitions in order to make a standard that is reproducible everywhere. And of course, we can also turn this on our head and use clocks as sensors for external fields. So understanding how external fields interact with our clock transition is a key area of the kind of research that's carried out in metrological institutes and elsewhere. So what about Rydberg states? Well, let's begin with magnetic fields, okay? So here I've written down the Zeeman Hamiltonian for a 1 electron atom, where I've kept the fine structure term. So for a 1 electron atom, I have a fine structure term like this with L.S, giving me the splitting between S and P states. And then I have my Zeeman term, which encapsulates the interaction with a magnetic field. So I have the Bohr magneton over here. And I can get and both the orbital angular momentum and the spin angular momentum coupled to the magnetic field, with, of course, the spin coupling twice as strongly as the orbital angular momentum, okay? So this Hamiltonian is identical to the Hamiltonian that you would have for low-lying states in the 1 electron atom. There is no difference here. I've neglected hyperfine structure, of course, which I've not included here. But again, that also doesn't depend on the principal quantum number. So none of these terms depend on the principal quantum number except for epsilon r here, which is the fine structure constant, which determines the size of the fine structure splitting. And that goes down as 1 over n cubed. So you'll recall that the spacing between the energy levels goes down as 1 over n squared. And so, sorry, the spacing of the energy levels is proportional to, the energy levels are proportional to 1 over n squared. So the spacing between them is proportional to 1 over n cubed. And one finds the same 1 over n cubed scaling for the fine structure splitting if you do the calculation. So basically in weak magnetic fields, I see exactly the same kind of Zeeman splitting as I would do for the low-lying states in my spinless 1 electron atom. The only difference is that if I apply a large enough field, this becomes equal to the fine structure, or I enter the so-called strong field or Paschen back regime at a much lower field than I would do for a low-lying state. So the take-home message here really is that for low magnetic fields, my atoms are about, my Rydberg states are basically have roughly the same sensitivity to fields as they would do for low-lying states. There is a bit more physics, which I don't want to go into too much detail about, but when you write down this Hamiltonian here, if you derive it, you derive it from the vector potential, and there is a term in A squared, which is known as the diamagnetic term, which we normally neglect. And if you rewrite that term in terms of the magnetic field, it looks like this. So it depends on B squared and R squared. And the way to think of this term is it's a term that's present in all forms of matter, whether or not they have orbital and spin angular momenta associated with them. And its origin is just the cyclotron orbits of electrons around the field lines. So if I apply a magnetic field to any kind of material, my electrons in there, assuming they're free to move in any way whatsoever, will begin to do some kind of cyclotron orbit. How free they are to move will determine the strength of the response. And this gives me this so-called diamagnetic shift to the energy levels. And what you find is that because it depends on R squared, remember R scales as n squared, so this term goes up as n to the 4th. So it becomes quite significant for Rydberg states. But practically you're finding you still need to apply relatively large fields of the order of a fraction of a Tesla before this term begins to dominate the energy level structure. But this was observed, has been observed in many experiments going back all the way back to the 1930s. So for small fields, we have the normal Zeeman splitting, the same as we would have for low-lying states. For larger states, we have to take into account, larger fields, we have to take into account both this fine structure scaling and the additional diamagnetic term. Now for electric fields, the Hamiltonian is obviously quite different. So electric fields, we write down this Hamiltonian known as the electric dipole Hamiltonian. So we have an operator here, the dipole operator, which couples to the electric field. And the dipole operator in a 1 electron atom, we can write down just as the position operator of the electron, okay? And so the first thing that we notice when we look at this Hamiltonian is that this operator has odd parity. And so the first order, the shift from this Hamiltonian is 0. So we have to calculate, if we want to know what happens when we apply an electric field to an atom, we have to do a calculation at second order. And if we do that, then we find the second order term looks like this. So we have, for example, the S states and P states coupled together. They have opposite parity, so they are coupled by this dipole operator. And we have on the bottom the energy separation between the P states that we're including in our calculation and the S state. And then we have to sum over all these P states to get the total second order correction. So this is just normal second order perturbation theory done on this Hamiltonian here. And if we do that, we find that the numerator scales as n to the fourth, because we have r here is scaling as n squared, so we square that, we get n to the fourth, and the splitting scales as 1 over n cubed. And so we find that this second order correction scales as n to the seventh. So whereas the magnetic fields for weak fields, we could basically just treat them exactly the same as low-lying atoms and largely forget about these corrections, this is just not the case for electric fields. Rydberg states are very, very strongly affected by electric fields, okay, because of this huge n to the 7 scaling of what amounts to being the polarizability. So what happens then when we apply an electric field is something like this. So this is what's known as a stark map. So here I'm measuring the energy or the detuning relative to the zero field energy. And here I have the electric field. Notice how small these electric fields are. Here I'm only applying a few volts per centimeter. So in this experiment, our electrodes were about 2 centimeters apart. And so we were literally just applying maybe 5 or 6 volts to the electrodes. And we can shift the energy of this state by gigahertz. So if you think about the size of the electric field, you would need to Zeeman shift the state by 3 gigahertz. You'd be looking at fields of many hundreds of, if not thousands of Gauss. Okay, so they would be quite difficult, quite hard to create in the laboratory. But here, just by literally collecting our electrodes, the equivalent of a battery, we can create enormous shifts. And we see the state doesn't just shift, but it splits as well. And that's because the stark shift depends on the modulus of the magnetic quantum number mj. Okay, so these are the 3 different mj states associated with this level: m equals 0, m equals 1, and m equals 2, and they have different stark shifts. And so here we have measurements, so the actual Rydberg lines made in our lab, that you can find them in this paper. And this is a calculated stark shift. And if we do the weighted average of all the different mj components in both the theory and experiment and compare them, we get incredibly good agreement between the calculation and the measurements. So here, the calculation, we're not doing perturbatively, we're doing a full diagonalization of the stark Hamiltonian, but you can do those kind of calculations in the ARC software that I referred to earlier. What you notice over here is that there appears to be some background. These states start to wiggle a bit. There's some extra stuff here. And this gray shaded area indicates what this is. This is the high angular momentum state. So remember, there are 55 other L states, which all have a stark shift, and they form a so-called stark fan. You can see that better in this plot from ARC. So here, all I've done is I've gone up a few in N, and I've increased the scale of this y-axis. So I'm zoomed out on the y-axis. So this is now roughly 60 gigahertz rather than 3 gigahertz. And this lets me see all the different states. My initial state, which will be this one, is this line here. And now I can also see all the different states with different quantum defects. So these are the states with low angular momentum. They have different zero field energies because they have different delta L's. And this fan here is all the high orbital angular momentum states, which have 0 quantum defects. So they all have the same energy here. But they begin to interact as we increase the field to cross or have avoided crossings with these low angular momentum states. And we get this diagram, which is called a stark map, which can be calculated again to very, very high accuracy. So why am I telling you about this? What could this possibly be useful for in an atomic clock, where typically we would want to minimize the effect of stray fields? Well, actually, working together with researchers in the group of Ian Hill at the National Physical Laboratory, we had to go at applying this to measuring stray electric fields in an optical lattice clock. So at the time, the MPL group was concerned that a shift that they saw between their strontium lattice clock and other clocks that they had in their group could be due to an electric field systematic. But there isn't really any way to directly measure that. So the idea was that we would do Rydberg spectroscopy in situ, so the atoms would be confined exactly where they would be in a normal lattice clock. And because of this n to the 7 scaling, we'd be much more sensitive to the field. And so we would be able to measure whether or not there was a field-induced systematic. And so our contribution was to calculate the stark maps. And in this case, it was absolutely critical to include the uncertainties. So here you see a theoretical stark map for n equals 75. Again, the 3 different mod mj components. With the band representing the uncertainty we have on the start maps. And those come from uncertainties in the measured energy levels. Not all the states, the Rydberg states in strontium, have been measured very accurately. And this gives rise to an uncertainty here. Once again, we did an experiment to compare these start maps with data. So these are measurements made in our laboratory where we know what the field is independently. So we have electrodes inside the vacuum. So this was a calibration measurement. And you see that the calibration agrees very well with the theory. And here there were no adjustable parameters. So then at MPL, they made measurements in their vacuum system. And the way they did that was to apply a magnetic field and measure the Zeeman splitting of the Rydberg state. So once again, this is the normal linear Zeeman splitting that you would expect for a D state in a magnetic field. So as I said earlier, there isn't really any Rydberg, any dependence on N for this. This is just exactly what you would expect. -2, -1, 0, 1, and +2, all with a linear Zeeman shift. But then when they applied a small field using some plates outside their vacuum system, you see that this nice linear shift this pattern is disturbed, okay? And you can see that in these diagrams here where you see that they're better fitted by a curve. But you can also, if you look closely, see that the spacing has been changed in these sections through the spectrum. So then what they did was they fitted this spectrum with a model that included the Zeeman shift and the Stark shift that we calculated. And you can see here that the fits were actually very good. And from that, they were able to extract the size of the electric field. And in fact, here I've just quoted the modulus, but it was possible to extract both information on both the size and direction of the field. So here where they applied the field, we had about 50 or 60 millivolts per centimeter. And here, which was supposed to be zero field, it was more compatible with about 15 millivolts per centimeter. So by carefully looking at the uncertainties in both the start map and the Zeemans and the fitting and everything else, we were able to show that using this method, we could reduce the fractional uncertainty in the clock frequency due to the electric field induced systematic to fewer than 2 parts in 10 to the minus 20. So in other words, by doing this in situ Rydberg electrometry, we were able to make sure that the electric field would not impact the accuracy of the lattice clock, even at the kind of 10 to the minus 18, 10 to the minus 19 level that modern lattice clocks are acting on. Rydberg states also interact strongly with blackbody radiation. Now, this was actually one of the first proposals for it, well, was the first proposal for how Rydberg states might be applied in optical lattice clocks. And the idea here was that it's well known that lattice clocks are strongly affected by blackbody shifts. And in fact, certainly for the strontium lattice clock, I believe this is the dominant systematic error. And the idea was that because Rydberg states are much more sensitive to blackbody radiation than clock states are, maybe if we make measurements of Rydberg states, we can cancel the, we can control the blackbody systematic much better. So it's the same idea as the electric field thing that I just discussed, but this time looking at blackbody radiation. And so how would this work? Well, the transitions, as we've already discussed, in the Rydberg region are split by a few tens of gigahertz, so in the microwave frequency region. And that's where the blackbody radiation has a much higher power density than in the optical region. So these Rydberg states have a comparatively large blackbody shift. The tricky thing is that they're basically all shifted by the same amount. So what happens is if you calculate their energies without the blackbody radiation, when you put the blackbody radiation in, they all shift by roughly the same amount. And you can calculate this shift, it depends on the temperature obviously, and they do that in this paper. It had been done previously, and you find that it's about 2.4 kilohertz at 300 Kelvin. So the idea then was that it would take some low-lying states, so this is the upper state of the clock transition, and measure from this state which isn't shifted. So for the clock transition, the shift is much, much smaller. So for the clock states, the shift is of the order of a couple of hertz at 300 Kelvin. So by measuring the energy between these two states, you would make a differential measurement essentially of this 2.4 kilohertz at 300 Kelvin. Now, to my knowledge, this measurement hasn't been used to constrain the blackbody radiation systematic error in a clock. And I think the main reason for this is that this accuracy is actually really challenging, not so much because it's hard to obtain a laser with 2.4 kilohertz line width. I mean, with combs, this kind of absolute accuracy is now routinely achieved, but more because in order to be measuring just the blackbody shift, you would have to control the start shift, which, as I just showed you, can be as large as gigahertz for even a few volts per centimeter. You would have to control the start shift to much, much better than we currently are doing, to try and get the start shift of the Rydberg states down to the same level as this 2.4 kilohertz. So I think it's an interesting idea that may have applications in future as we increase the precision with which we can control the electric field in these Rydberg spectroscopy measurements. But I think this is the principal reason why it hasn't found use in controlling the blackbody errors in current clocks. So I just want to say a few words about another favorite systematic error that clock scientists worry about is, of course, collisions. This is particularly something that has vexed people working on atomic fountains. And as far as I understand, it is in fact the dominant limitation on the systematic accuracy of atomic fountain clocks. So what about collisions between Rydberg atoms? Well, as you might anticipate, given that Rydberg atoms are several hundred or if not several thousand times larger than ground state atoms, the situation for Rydberg atoms is not very good, and collisions are a problem. And there are a huge number of different collision channels, but one of the most dominant ones is that you take two Rydberg atoms and they collide. One of them, sorry, there's a term, one of them, there's an SR missing here, SR plus missing here, sorry. So one of them is ionized, creating an SR plus, and the other one goes to a lower Rydberg state or lower lying state, and an electron is produced. And this process is known as Penning ionization. And the cross section for it basically scales as the size of the Rydberg atoms. The area of the Rydberg atom again, because cross section is of course an area, and this again scales as n to the fourth. So this should be r squared. The problem is even worse, because what happens is these electrons can get trapped by the ions to form what's called an ultra-cold plasma. And then the electrons collide further with more Rydberg atoms, ionizing them and creating more electrons, and you get this runaway avalanche ionization of the gas. And so Rydberg experiments with randomly distributed gases of Rydberg atoms, so MOTS, for example, are always accompanied by some ionization. And if the density is large enough, then an appreciable fraction of the gas can become ionized within a short space of time. And this has been studied for quite a few years, and these ultra-cold plasmas are now a subject of research in their own right. So here's some data again from our lab showing just how bad this effect can be. So this top graph shows the number of ions that we detect on our microchannel plate. And here we're applying a laser resonant to the, slightly off resonant to the Rydberg state. And you see that as we apply the laser, we get a huge increase in the ion signal. And this is accompanied by a very fast drop in the number of atoms in the cloud. And this eventually settles down, and we see these long-lived Rydberg atoms here, which have lifetimes much longer than this 100 microseconds that I mentioned earlier. They can live for milliseconds. And what happens here is that these states have ended up in high angular momentum states, so states with high L, and these states can't radiatively decay very quickly to the ground state because they have to do many, many, many dipole transitions to get down there. And so you basically end up with your sample being contaminated by these long-lived Rydberg atoms, even after this fast loss. And this data here just shows the idea of this plasma effect. Here we're increasing the number of atoms in our cloud, and you see as we reach a certain threshold density, then the number of ions that we detect just takes off, and that's because this plasma has formed. And now this process here where electrons collide with the Rydberg atoms is strongly favored, and the gas just ionizes. So this might all look very pessimistic for doing anything interesting like entanglement and squeezing, and indeed it is very difficult to do anything interesting like that in a cloud of randomly distributed atoms like in a MOT. So let's move on then to the other types, non-collisional types of interactions between Rydberg states. So the situation that we'd really like to have for Rydberg atoms is actually this one, where we have, let's say, two traps for the moment that confine the atoms and keep them well apart from each other, so we can't get these collisions that I've just described. And we'd like this separation to be bigger than the orbital radius, than the size of the Rydberg atom, so that we recall that was about 200 nanometers. So ideally we want a pair of traps separated by a few microns, okay? Now, normally, if you were dealing with ground state atoms, then this would basically be hopeless. Essentially, there is no interaction between ground state atoms at this kind of distance. This isn't, however, the case for Rydberg atoms. So how do they interact over such long distances? Well, the physics is that it's a dipole-dipole interaction. So an induced dipole on this atom is going to interact with an induced dipole on this atom, okay? So the interaction potential or Hamiltonian looks a bit like this. There's an angular part. This is the product of a dipole operator for this atom and a dipole operator for that atom. And we find that this dipole-dipole interaction scales as 1 over r cubed. And again, this is 0 to first order due to parity. The dipole operator has odd parity. So you find that there is no dipole-dipole interaction to first order. And we have to do the calculation to second order as we did for the electric field. And I won't go through this, but basically you do exactly the same thing again, second order perturbation theory. And what you find is that the interaction has a distance dependence that goes like 1 over r to the 6th. That's just 1 over r cubed times 1 over r cubed, because it's second order perturbation theory, I have the square here. And this is known as a van der Waals interaction. So this is the same van der Waals interaction that I get between atoms in their ground state. Essentially, it's the same mechanism. But the key result is that when you put the numbers in and look at these scaling laws again, you find that this C6 coefficient that describes the strength of this van der Waals interaction scales with this absolutely astonishing power of n to the 11. So this is one of the strongest scalings that I know of in physics. And what it basically means is that we have a situation like this. So here I plotted the van der Waals interaction between strontium atoms in their ground state. So here we find that it's 10 to the minus 5 hertz. So even just about measurable in optical lattice clocks over this distance, potentially in the future, but even so very, very difficult to measure. And then if I excite the atoms to n equals 80, which I can certainly do, this is routinely done in experiments, then I turn on this interaction, which is 19 orders of magnitude stronger, okay? So really I go from a non-interacting situation to a very, very strongly interacting situation. And even at distances of 10 microns, I have interaction strengths of about 10 megahertz. So this can completely dominate the energy scale associated with atomic clocks. It also completely dominates the energy scale associated with the motion of the atoms, okay? So we can really enter a very strongly interacting regime where this van der Waals interaction is the dominant energy scale in the system. So in the next section, I want to talk about how we use this strong long-range interaction to create entangled and squeezed states. I'm not going to go into great detail about what these are or about their applications, because there was a very nice talk from Luca, and I'm terribly sorry I forgot the other speaker's name yesterday, which outlined exactly how these states can be used.
Daniel Benedicto.
Daniel Benedicto, thank you. I'm very sorry. I watched the talk and I really enjoyed it, but I have 2 young children. I don't get very much sleep, and so my memory doesn't work anymore. But I refer you to their talks for more details about the background to do with these things. Here, I'm just going to focus on the application of Rydberg states to generating these kinds of states in optical clocks. Okay, so here we go. Here's the situation that we said we wanted. So we have 2 atoms, well isolated, trapped, for example, separated by a distance of 5 microns, let's suppose. And the idea of how this creates entanglement goes back to this very famous paper by Misha Lukin and collaborators in the early 2000s, which now has probably nearly 1,000 citations. So it's one of the kind of seminal papers in this field. And they propose this mechanism known as Rydberg or dipole blockade. So how does this work? Well, the idea is that if I imagine driving this atom from the ground state to the Rydberg state with a laser, then if I drive both the atoms at the same time, and I can't tell which atom is which, so if my laser beam overlaps both the atoms here, then if I write this in the so-called pair state basis, then I go through the states in a ladder like this. So my initial state is both atoms in the ground state. And then I have a state where one of the atoms is excited and a state where both the atoms are excited. And so if I do this properly, if the atoms are indistinguishable, I have to write down either a symmetric or an anti-symmetric superposition of the left-hand atom excited or the right-hand atom excited. And you can show that the anti-symmetric superposition, so the one with a minus sign, doesn't couple to light. Again, this comes from parity. It's not coupled to the state 0, 0. So the first excited state in my two-atom system is actually this state R0 plus 0R. And that state is actually an entangled state. And normally I'm allowed to go on from this state up to RR. And you can show that the resulting state, which includes both this and that, is a product state and it factorizes. And so normally when I'm driving atoms that don't interact, I don't see this entanglement, okay? But the idea with the Rydberg blockade is that the interactions become so strong that they exceed any line width associated with the transition, whether that's the radiative line width or the line width, the power broadened line width associated with the Rabi frequency. And at some distance between the atoms called the blockade radius, this interaction begins to exceed the line width. And this transition rapidly goes off resonance. And so essentially the atom ends up stuck. It can't reach this doubly excited state RR. And so now instead of driving Rabi oscillations with two independent atoms between 0 and R, I'm actually driving my pair of atoms between this state 0, 0 and this entangled state R0 plus 0R, okay? So if I do a pi pulse and I stop here, then I've created an entangled state between my two atoms, okay? So how might you do that in practice? Well, one of the most powerful ways to do this kind of experiment is using something called an optical tweezer array. So here's a cartoon of how this works. So basically you use a high numerical aperture lens to focus a laser beam down to make a very tightly focused dipole trap with a radial sort of width of about a micron. And these traps are so small that they can contain just a single atom. And then by sending multiple beams through the lens with different angles, I can make an array of these traps. Okay, so I can end up with an array of traps, each one with a single atom in it, separated by a few microns. And so then this is how this might look in a clock. So I have the strong cooling line for readout of my ground state, and I have the clock transition as a kind of a qubit, and I can couple these Rydberg states together between the atoms in these tweezers. Okay, and I can put importantly, I can put many tweezers inside this blockade radius. Okay, so I can create an entangled state that can encompass many atoms at the same time. And this tweezer array Rydberg blockade thing is now very well developed in the alkali atoms. It's been going on for at least 10, 12 years now, and it's been used to do some incredibly beautiful experiments on Rydberg quantum simulation with, I think the record is still about 50, 60 atoms in a Rydberg quantum simulator, simulating spin systems using this ability to create entanglement. You can find out more in this really nice review article. But I just want to show you quite how much potential there is in this. So this is work by the group of Antoine Broes at Institut d'Optique. So he's one of the authors of this review. And there they use a spatial light modulator to make their tweezer arrays. And this technique is a holographic. It essentially writes a phase on the laser beam that goes through this lens. And because of that, it's possible to make not only 2D, but 3D arrays of these traps. And they've developed the techniques necessary to image them with single atom resolution. And the pictures you see here are images of these arrays. They're averaged over many repetitions of the experiment so that all the traps are filled. But the pictures are real atoms trapped in these lattice sites. And you see that they can make incredibly wide range of 3D geometries separated by a few microns. So this is about 100 microns across these cubes. And they can make beautiful shapes, fullerene-like shapes, toruses, Eiffel Towers, you name it. So this is an incredibly powerful technique that's very well developed for the alkali atoms. And in it, they've used the Rydberg blockade to make really quite complicated entangled states. But it's just moving into the clock community. So I want to talk a little bit about this paper from May this year from the Andres group in Caltech. So a couple of years ago, two groups in the US, Andres group and Kaufman's group, made one of these tweezer arrays trapping single atoms for strontium for the first time. It's now been done for ytterbium in Princeton. I think there may be a group in Korea that's also done it, which I should have listed here. And this year they published for the first time the creation of entangled states in this system using Rydberg blockade, okay? We're working towards doing similar experiments. So we have single atoms trapped in an optical tweezer as well. My group is giving a poster tonight where this is a picture of a single atom. So if anyone asks, strontium atoms are white and square. Then you can find out more about it in the poster. But coming back to this work, beautiful work, absolutely beautiful work from the Andres group. So here's their system then. They have a clock transition, and then they couple the clock transition up to the Rydberg state. And for the moment, this is what they're going to be trying to create entanglement on, this transition here. So they're just going to use the clock transition for state preparation, putting the atoms up in this metastable state. And they can detect either the using fluorescence, or they can ionize the Rydberg state using an extra laser. This is a technique that we pioneered in my lab, but it works very, very well. And they create two kinds of tweezer arrays. So these tweezers are at the magic wavelength for this clock line. So this is exactly the same as a lattice clock, if you like. But now we have an array of traps, in this case in a line. Here they're separated by 11 microns. This will be the non-interacting case. And here they've created little pairs like this, where in each pair the traps are separated by 4 microns. And then there's a bigger gap to the next pair and so on. So they can do experiments on pairs of atoms, on many pairs in parallel. Okay, so this is just a completely different paradigm now for doing clocks, where we have magic wavelength tweezers instead of magic wavelength lattices with single atom control. And so these are the kind of results they get. So here we're in the non-interacting case where the atoms are far apart, and they drive Rabi oscillations between the ground and the Rydberg state. And they get this Rabi frequency omega. And down here, they're driving interactions now, Rabi oscillations now, not between G and R, but as I said before when I described the Rydberg blockade, between the GG, the double ground state for this pair of atoms, and the Bell state 1/√2 GR plus RG. Now, as you can see, they have incredible coherence for driving these Rabi oscillations towards the Bell state. And proof that they're really coupling to this entangled states comes from, if you look carefully at these oscillations, you should be able to see that they're much closer together here than here. In fact, this is a factor of √2, and that's related to this √2 that appears out here. The Rabi frequency is √2 times higher for coupling to this entangled state than it is for driving the single atom transition. And from these results, they show that they have an uncorrected fidelity, so without correcting for any state preparation or detection errors of 98%. Which is just remarkable, and which is starting to put neutral atoms on the kind of territory that superconducting and ion trap systems have been exploring for the last 10 or 15 years. Now, the problem with this is that the blockade mechanism produces a so-called W state. So there's only one atom in the Rydberg state, and these particular states have no gain in the quantum metrology experiment. Okay, they don't improve your sensitivity. As we learned from Luca and Domenico's talk, it is a squeeze state that we want. And so we can produce that using this kind of Hamiltonian, which is known as a one-axis twist, where we have this spin-spin coupling between neighboring atoms, okay? So can we engineer that with Rydberg states? And the answer is yes. So this was first worked out in this paper by Isabel Bouchol and Klaus Molmer. And the neat way to think about this so the way to think about this is the following. What you do is you detune your laser from resonance with the Rydberg state. So instead of driving on resonance like you do in the blockade, you detune here. And what you do in a non-interacting case is you have an AC Stark shift that creates an AC Stark shift. It's just like having an optical dipole trap, okay? And again, you can derive this AC Stark shift for a pair of atoms, and you find that there are terms which are related to the state R, and terms which are related to the pair state RR, and if you carry on going, there will be terms related to RR, etc. And if you add up all these terms here, a miracle happens, and the answer is that you get the same as what you would get if you just count a single atom, okay? So the fact that the AC Stark shift is the same for n atoms as it is for one atom, you can view as actually a fortuitous cancellation between different parts of this AC Stark shift. So for the experts, this is known as the Dickey state basis, okay? So if you do the calculation in the Dickey state basis, you find it is the same as the single atom basis. Now the Rydberg blockade gets rid of these terms, and so that's no longer the case, and you have this extra term which depends on n squared. And this n squared term corresponds to a spin squeezing type Hamiltonian. Okay, so this n is telling you that the AC start shift now depends on whether the neighboring atom is in the Rydberg state or not. So I have a distance dependent correction to my AC start shift term, and this energy shift here is going to give me a spin squeezing like term, and that was first realized by these authors. So a few years ago, together with a group of Thomas Pohl then in Dresden, we actually worked out what this would do in a lattice clock and showed that you could apply the sequence of pulses here to produce a spin squeeze state, which can then be used in the interferometer, as was described in the talk yesterday, to create a spin squeeze state. And so this detuned coupling to the Rydberg state is known as Rydberg dressing, and we did some experiments in Durham where we used a cooling transition rather than the clock line, but we were able to show that we could dress for long enough without having these collisional losses to actually trap some dressed atoms here. So these atoms here are actually the ones that are not in the dressing laser beam, and they fall away from the trap, and the ones that are left behind are the ones with this small admixture of the Rydberg state, these Rydberg dressed atoms. So this looks like it should work in a clock without too bad losses, and we await results either from the Caltech group or possibly even from our group on how this might work in practice. Okay, I'm a little bit over time here, so I'll just briefly summarize. Rydberg clocks could be really interesting for systematic errors. We've already shown it works for electric fields, and blackbody radiation is a possible direction to extend this in. The Rydberg clocks seem very powerful for creating entanglement and squeezing, and by extension, quantum metrology and simulation in the optical clock platform. Very quickly, a couple of interesting perspectives. People are doing Rydberg physics in ions now, so it's not just neutral atom clocks that this could be useful for. And this paper came out this year, where they've created a very fast, very long-range gate between trapped ions using basically the dipole blockade between Rydberg states of ions. Okay, so more is certainly coming in this direction. And we've also been exploring in my group how these Rydberg states might be used for fundamental physics. So there's growing interest in using clocks and precision measurement to constrain physics beyond the standard model, and Rydberg states have some important applications here, essentially because you can change their length scale there versus at length scale of any new physics interaction. So I just want to thank my team. These are some of the guys who did the work. Jean Jarjou, who's not in this picture, is also in my group. Have a PhD position available for, and I just want to thank you all again for your attention.
Thank you, Matthew. So we can quickly go to the question and answer. So please raise your hand for any question you can have. In the meanwhile, I have two questions by Stuti Gugnani that was question related to the Starship and Blackbody radiation. I can read for him. A bit of basic question. What method do you use for applying the electric fields when you measure the sensitivity of electric field? And then, as I understand, you were able to cancel out the effect of a stray field, and thus can work with them being there, because they can be pretty important for Rydberg states. So if you can reply to.
So the electric field was just applied using metal plates, basically connected to a wire, so the electrodes essentially. So in our experiment, those are inside the vacuum. In our experiment, the mop coils are mounted inside the vacuum, and the electrodes are just two rings, one on each coil, and the rings are segmented to allow us to apply electric fields in any direction. And then they're just connected to a DC voltage source. And in the case of the MPL group, when they built their lattice clock, they obviously didn't put electrodes inside, but they were able to apply the electric field from outside. So it does get affected by the dielectric constant of the glass somewhat. But again, because we were able to determine that field in situ, that turned out not to be a problem for the experiments, because we'd already calibrated the start shift and the calculations in Durham. Yeah, concerning the cancellation, I am very interested in the question of how accurately one can measure the absolute energy of a Rydberg state. And I don't actually know the answer at the moment. So that will depend on how well you can cancel the Stark shift. And that's not a direction that's been pursued with cold Rydberg atoms so far. So I think it's an interesting question, quite how far one could push this. And can you get down to a level, for example, where this Blackbody shift could be measured? And by extension, that is important for these new physics experiments. If you want to measure new physics using Rydberg states, you need to control the Stark shift at this kind of kilohertz or better level of precision. And I think it remains an open question whether that can be done at the moment.
Okay, thank you. So since we are a little bit late, if there are no any more questions, I would thank Matthew for his very interesting presentation. And I reported in the chat the link to the next talk by Stefan Schiffer. And we have a 5-minute breaks, and then we can start again with the new session in 5 minutes. Thank you, everybody.